All right, Huskies, I hope that this video finds you doing safe things and keeping yourself well. And I want to get you guys excited about the fact that we only have 2 more videos to go. And what we're going to be talking about today is about partial fractions. And this partial fractions category is going to dominate our conversation for the next couple of days, for this one and the next one. And what it really comes from is it comes from the idea that partial fraction, it should really call it partial fraction decomposition. Decomp. Now, when we say something is going to decompose, that would mean that it's going to go from a larger idea, a whole, and it slowly but surely breaks into smaller parts and becomes smaller pieces of the whole. That versus the idea of composition, which is taking smaller pieces together and combining them to make a larger whole. Now, the reason why I bring up these two individual words, decomposition and composition, is because we have done some compositions in the past. And those particular compositions were something that we did in Algebra 2. We probably should have done them in Algebra 1. And that was the composition of two fractions that we would add together to make two combined ideas. So let's say we had two of them with two separate denominators, and we wanted to either add or subtract those fractions to get something together. So a composition like x over x minus 1 added to 3 over x minus 2. Now, if we were going to add these two fractions together, and I'm just going to go back to Algebra 2 for a second, we would probably say that each one of these needed a common denominator, like this one needs an x minus 2 top and bottom, and this one needs an x minus 1 top and bottom. And then we would ultimately be able to say that those two ideas would be able to be combined into one solid fraction like x minus 2, x minus 1 on the bottom, but the top would be a combination of these two numerators pushed together to make that idea. So we would get a 3x there and a 3x there, so maybe 6x. And then this would be negative 2. Oh, no, excuse me. Hold on a second. Let me erase that. So we would get x times that, which would be something like x squared, excuse me. And that would be a negative 2x and a positive 3x or a positive 1x. And then last but not least, we would get something like minus 3. Now, what you've done right here is in Algebra 2 is you did a great job of composing two smaller ideas together to make a singular fraction. But the thing that we're really always concerned about in math is that this is one directional. We never really focused on it in terms of trying to decide what to do in algebra. We're just like, oh, okay, that's how you do that. But there is a arrow that goes in the opposite direction. And this would be taking something that's a singular unit and finding a way to decompose it. Or better yet, make it into two smaller partial fractions. So our job today is to figure out how we can make this arrow go the other direction. So here's a quick question. We've got ourselves a put together entire amount of fraction that has all of it put together as one fraction. But what we want to do is decompose this into two smaller fractions and make it into some partials. Now we can probably recognize that there is probably one fraction that's got an x minus 2 in it and another fraction that's got an x plus 1 in it. And you're absolutely right. Those are going to be the two partial fractions. But the real question boils down to here is what should I do in the upstairs component? I mean, what ends up being up there so that if we did the common denominator idea like we did up above, it would generate the 11x minus 10. Now, to do these partial fractions, or why we do these partial fractions, let me just say that this is just not a random section. In a lot of stuff that we do in calculus, you will be ending up with ugly kinds of combined functions, and you're going to have to find ways to break them down into smaller individual parts. Mainly, this falls into the category referred to as the chain rule, which is where we see functions that are within other functions, Or we might even see it in integration where there is partial fraction integration too as well. And this will relate back to that concept too. Now, to find a partial fraction combination, what you're going to have to do is you're going to have to follow a couple of mainstay rules, okay? First off, there's going to be a setup section to this partial fraction decomposition. Now, when I say that there's a setup, there are really 4 types of setups that you're going to have to be associated with. And I'll discuss each one of those 4 types as we go through the next 2 videos. I'll get through type 1 and type 2 today. Then there's going to be a multiplication on both sides to eliminate the LCD, some simplification that we'll do, some equating, and some solving that's going to be done at the end. Now, I'll go through each one of those steps as I do one of these so that you can see all the different types that are going to be adjusted with those, okay? Now, type 1 partial fraction decompositions are going to be relatively easy to identify by the fact that we're going to be looking at some denominators here that will constitute what I would call real answers. I mean, they are real rooted answers. If I set x minus 2 equal to 0, I get x equals 2. This is a real root kind of answer versus something that was on the bottom that might end up giving you imaginary roots, or maybe it's prime. Those will fall into other types. So if you see stuff that is broken down into individual, unique, and that's probably the best word to say here, unique answers, then you're going to be dealing with a type 1. Now, the way you set up a type 1 partial fraction decomposition is that you're going to recognize that each one of these unique answers, the unique roots on the bottom, is going to be one of the possible denominators that you're going to see underneath. Now, I always put a plus in between these, but they later can be ideas about subtraction, but it's primarily going to be something that goes on in the numerator that's up above. Now, you're going to separate the denominator into 2 separate unique values, and in a type 1, you're going to put an A value upstairs on this one and a B value upstairs on this one. You absolutely have no idea what those 2 numbers are supposed to be, and that's what the solving part's going to be. So a type 1 is always set up with a broken denominator, and you're going to end up putting A's and B's in the top. Now, the setup part is taken care of. That takes care of our very first piece here. You set it up correctly. And I'm even going to take this one over here and say this one is unique too as well, has unique binomials. We would set it up exactly the same way. X minus 4, and then a plus sign, and x plus 2, and we would end up having A and B in the top, all right? So you can recognize, like, okay, I got a type 1. I can figure out what those values are. Now, let's talk about what the second step here says. It says that we need to multiply both sides by the least common denominator. Well, the least common denominator is this value that's on the bottom right here. And I'm going to multiply each individual side by that entire denominator. So this one's going to be x minus 2 and x plus 1. And this one's going to get multiplied by x minus 2 and x plus 1 also. Now, on the left-hand side, not a whole lot really is super exciting about what happens. If I multiplied by this common denominator on one side, and this was the already common denominator on that left side, they would completely cancel with one another, and the left side would be 11x minus 10. That would be no big deal. Now, that always happens, and I'm going to institute that. It always happens that the numerator is all that's left on the left-hand side. It's the right-hand side where some really interesting things take place. Now, I'm going to do this in 2 different colors. This one is orange, and this one is kind of like a pink color. And I'm going to say, what if you multiplied by this common denominator on each one? Now, if we introduce the idea of the orange one, this common LCD multiplied by this one would end up canceling the x minus 2's in that regard. And ultimately, it would be the A would be multiplied by whatever was left over in that LCD, which is x plus 1. And that would be the part that would be for the first partial fraction. Now I'm going to put a plus sign, and now I'm going to do this with the second one and go multiply this one by the least common denominator, and it would be a different cancellation that this one would cancel with this one, and the leftover amount would be b times x minus 2. Now, what you're seeing there is a partial cancellation that's taking place of a distributed least common denominator. Now, if I continue to simplify this, and that's our third step going on here, I get 11x minus 10 would equal, and that would be ax plus 1a plus bx minus 2b. And all I've done there is distribute the b's and a's through here. And people that are really organized at this will be very successful at doing partial fraction decomposition. Now, 11x, I'm going to continue to simplify a little bit. And what I'm going to see here is that there's some things that are like ideas and things can be taken out of them. And I can really focus on the fact that these two concepts right here were both affiliated with x. And if I wanted to, I could steal an x out of them. I'd pull them together next to each other, steal an x out, and I'd be left with a plus b in that location. And that would take care of those two ideas. Now, these two last ones are based on constant values, and they're similar in the fact that they're just constants. And I'd be able to say plus, and that would be 1a minus 2b would be the other possible constant. Now, the reason why I've done such a thing is because of the next and the fourth part of our deal here. We've simplified it. Now what we're going to do is we're going to do a section where we equate coefficients of x and constants. Now see this piece right here. It is affiliated with the x amount that's going on right there. If I was really to write it better, I'd probably say that a plus b is times x and put the x on the other side. And if I want to equate, this a plus b is really technically in the same location as this 11. And what that equating allows me to do is to write a separate equation about a and b. That a and b, ultimately, if I'm going to equate that the left side is equivalent to the right, would be equivalent to 11. That those two right there would be equivalent to the coefficient of the left-hand side. Now I could do that same idea with the 1a minus 2b. This is a constant term, and the constant term of the left side is negative 10. And I'd be able to write that a minus 2b would be equal to negative 10. Now, your purpose in this was to find coefficients or find values for the variables that you set up, a and b. And ultimately, you set up two equations with two unknowns, and now you can see where that elimination effect is going to take place. I'm going to multiply the bottom row or bottom column by a negative all the way through it, and I'll add the columns together and end up with 3b is equal to 21, and ultimately that b is equal to 7. Now, I could recycle this idea back inside here and also come up that a happens to be 4, and these two individual values are incredibly important in helping us write the final partial fraction decomposition. If you remember all the way back up here to the beginning, you wrote that a was over x minus 2, and that particular case it would be 4 added to 7, which is the b value, over x plus 1, which is our original setup, and this represents the partial fraction decomposition of the original LCD kind of fraction. So we've gone from one fraction to two partial fractions that add up to the same concept. And you've still got an equivalence. If you really wanted to, you could multiply top and bottom of this by the same common denominator thing again and do what we did up above in a composition, and it would return back to the original concept. Now, what you've done there is found an equivalence, a partial fraction equivalence. Now, it had a lot of steps to it. And I want to make sure that we didn't miss anything and you don't get lost in the process, because there is a lot of little algebra that's going on right here. Now, let's take a look at the second example. I'll lead you through it one more time, and you'll get the idea of what we're trying to accomplish. Now, to do this, we would again multiply by the common denominator on both sides, x minus 4 and x plus 2. And this one would be multiplied by x minus 4 and x plus 2. And then we do the cancellations and figure out what we've got. Well, it will cancel everything. We'll get x plus 14 is equal to, and we only get partial cancellations of this particular stuff in here. So we get a times, well, the x minus 4s would cancel. You get x plus 2. And then the b would be multiplied by not x plus 2, but the x minus 4, the leftover component of that one. Okay, now this is all about simplification and combining terms that seem to go together. That's x plus 14 is equal to ax plus 2a plus bx minus 4b. And we'll put the x pieces components together. Now, it is very common for us to lose sight of what the left-hand side is doing. It's kind of like it's being drawn down. So you might see me like start to forget about it for a little while because it's really the right-hand side that really has anything to do with stuff. And that's 2a minus 4b. And I'll put that back over here, x plus 14. Now, my two equations would be about a linear a plus b is going to equal the coefficient in the front of that one, which is 1. And then a 2a minus 4b is going to end up being the constant value, which is 14. And a little solving going on here. If I multiply this bottom guy by, let's say, positive 4, we'll eliminate b's. That would be a 4a and a 4b and a 4, like that. We'd cancel the b's, and we'd end up with 6a is equal to 18, or a is equal to 3. And in a recycling concept, if I recycled that back into there, a plus b is 1. So that would mean that b would have to be negative 2. And check my work there. Make sure that we're in good shape there. I'm going to erase some of my stuff there. Yeah, I think that would be the case there, that a plus b would equal 1. And ultimately, we would end up with a constant concept of negative 2. Now, what would be the partial fraction decomposition? Well, that would end up being 3 over x minus 4, and I'm doing that right here, sorry, just to make sure you can see it, plus, and you could probably say that this is not necessarily a plus, and this might be something you want to watch in Math Excel so that you don't miss this. It could be written as minus 2 over x plus 2. So pay attention to how the minuses are working in your numerators so that you're consistent with your Math Excel. Now, that takes into consideration how you do a type 1 type of question. Okay, I had to cut a whole entire section of video out because I'd lost the deal from it. It completely disappeared. I don't know why it keeps doing that. And here we go. I'm going to try the second type right now. Okay, so here comes the second type one. So the first type one that we were dealing with, it turned out that what we were dealing with on the bottom were distinctly unique answers. Well, it turns out that we can have distinctly unique answers, but sometimes they can actually be repeated. And if they end up turning out to show repeats to them, we have to take into consideration that those repeats could be individualized partial fractions as well too. Now, here's what I mean. You can easily identify a repeat in the fact that it has been shown that it's not showing up just as one individual binomial, but it is a multiple of several of them. Okay? Now, the way you set these type 2s up is that you have to take into consideration every single way that that repeated linear factor could have been written. Well, we're going to start with the letter x out here. That is distinct. It's going to be x equals 0. It is not got a repeater on it or whatsoever. So the very first one you're going to write is a over x. And that'll take care of that particular value. Now, this one right here, which has got a repeat in it, could end up being that you could be doing x minus 3, or you could be x minus 3 quantity squared. So it dictates that you need to think about all the possible ways that one can be done, and in all their descending possibilities. So this would be b over x minus 3 and c over x minus 3 quantities squared. Now, if it turned out that you had one that was like an x cubed on the bottom, like say x minus 3 to the third power, you would have an a over x minus 3, a b over x minus 3 squared, and a c over x minus 3 quantity cubed. So what you end up doing is that you have to show all of the possible reiterations of that repeated concept over and over again. Now, if you have those repeats, this is the way you set up a type 2. They're distinctly unique, not meaning that any of things are prime. They give you individual values, but they might have repeated values in terms of a larger power on the outside. And that's the way you set up a type 2. Now, the process to solve these is done exactly the same way. You multiply each side by the common denominator, which is x minus 3 quantity squared. And again, it'll cancel everything on the left-hand side. And you end up with x minus 18. Now, if you do that concept over here, you're going to get x times x minus 3 quantity squared being distributed in each one of these three different cases. Now, if I do the one over here with the first case, I'm going to have a is going to be multiplied by, well, the x's will cancel, but the x minus 3 squared won't. So we'll get x minus 3 squared here. In the middle, we'll get the b, but it won't cancel the exterior x. So we'll get bx, but then it'll cancel one of the x minus 3's, and we'll get one left over x minus 3. And then in the last case, the x minus 3 squareds will cancel, but we'll get the c times the x. So you have to make sure that you're catching every single one of them so that you get this part correct. Now, here's where your algebra really does kick in. And as a reminder, this would probably be better written as x squared minus 6x plus 9 instead of the squared, and then distribute the a through. So we've got ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx. Okay, now again, I'm going to leave the left-hand side alone for a second and really look for things that are like ideas. And this is where really maybe a color coding system really does help. These two are both x squared concepts, and ultimately, if I stole the x squared out of them, I'd be left with a plus b, and that takes care of those two components. Now, if I try a different one, this one is an x term, this one is an x term, and this one is an x term. Those three could be an x stolen from all of them, and I always use plus signs in between here, x times, and now if I stole it out, it'd be a negative 6a minus a 3b, minus 3b, plus c would be the linear values, and then last but not least, we'd be looking at constants, which looks like that guy's the only one, and that'd be plus 9a down here on the end. Now, again, remember that our left-hand side was x minus 18, and once you've got it broken down like this, you can start to equate values that are in the inside the parentheses to the coefficients that are on the other side. Now, here's the problem. We don't have an x squared one over here. You're like, where's the x squared one? I don't know. Well, that's because it's a 0x squared, and the equation that we would be ultimately writing out of that would be a plus b would equal 0. Okay, so that's our first equation. Next equation would be about the linear piece, which is equal to 1. That's negative 6a minus 3b plus c is equal to 1. And then last but not least is the 9a, and the 9a would equal negative 18. Now, when you start to get multiple equations like this, especially with a, b's, and c's, you're going to want to start to thinking about how do I handle them in terms of their solving. Now, in a lot of cases, you might be able to solve one relatively easily. Like you can see that a is going to be negative 2, and that would be coming from this equation. A being negative 2 would make b equal to 2. And then last but not least, you'd solve for the last one, which would be negative 6 times negative 2 minus 3 times 2 plus c is equal to 1. And we'd end up getting, what, 12 minus 6 plus c is equal to 1. Well, that's 6. 6 plus what would be equal to 1? Well, c would be negative 5. And now you have all the components that are necessary to write the partial fraction decomposition with all of these coefficients back up here in the original, which would be like negative 2 over x plus 2 over x minus 3 and negative 5 over x minus 3 quantity squared. And that would be your partial fraction decomposition. Okay, now what I'm going to do is give you guys a little bit of time. I'm going to pause right here and have you guys figure out how to do this one that's next door. Move it over here just a little bit, and I'll show you the work in just a moment. And wow, poof, a whole lot of work just appeared on you, and you should check this out. So first off, set it up as a repeater, type 2 repeater, and we ultimately will see that we multiply each side by the common denominator, ended up canceling on the left like we expect. The distribution of it on each one of the 3 partial fractions ends up giving you a times x minus 1 quantity squared, the bx times an x minus 1, and the c times x. Combining our distribution across this trinomial, remember we want to take care of that ahead of time, and then distribute the a across it, then combine your like ideas together, factoring out the x squared or x or the constant, and we end up generating 3 equations. Now, one of them happened to be a equals 2. That was just this one. A plus b is equal to the x squared part, which isn't there. That's 0. And the middle guy was equal to the coefficient of 1 that's on the front of the x. And you end up solving, getting 2, negative 2, and 3. Now, the thing you need to be real cautious about is that these equations that you end up generating on the end can ultimately get a little bit more convoluted, especially if the partial fraction ends up not canceling a whole bunch of stuff. But you get to get an A, B, and C, and this is where you could use an augmented matrix, or RREF, and solve using your calculator. Now, hopefully, we'll get a chance to see one of those in this section that we're coming up to, and we will try a non-repeating prime quadratic factor, and we'll come up with this guy in just a second. I'm going to stop right here at number 5 because this one ends up being a type 3 question. And I'm going to pick up here on the second video with example 5 and push forward with the rest of those on how to handle a type 3 and type 4. So on the type 1 and type 2, everything is a distinctly answerable root. And if they are distinctly different, just A's and B's. But if you end up having a repeater, type 2, we end up doing distinctly A, B's, and C's, but you got to make sure that you cover all the different possible choices of repeater. So give these a shot tonight, and we will work it out from there. Okay, I didn't really feel happy with the ending of what I'd come up with. I did want to speak to the idea about the RREF for the end of this question. I'm going to go back to this one right here in example number 3 and talk about these 3 equations that are stated right here. Now, what I want to state on this is I really want to talk about how could RREF, or when these equations start to get more difficult, how could I use my calculator to come up with a technique on solving that would be a little easier, especially if there's 3 variables, 3 equations, or even maybe even 4. So let's kind of talk real quick about how I would handle a calculator version to this one. And I'm going to think about how RREF is going to work too. This is something that we discussed in the prior idea. Well, first off, you would want to take these 3 equations and write them as an augmented matrix, with the answer matrix being down here on the end of the 3. Now you can see the answers are relatively easy to find, so we know that this would be 0, 1, and negative 18 on the end of this augmented matrix. But what would this interior piece be? Well, this is your ABC concept that's going on here. And up above, you can definitely see on the first one, it's an A and a B, but no C. So it would be a 1 for the coefficients of A and B, and a 0 for the C value. If I was talking about the next row, -6, -3, and 1 for the part for the second equation, and then a 9 only for the A, but the B and C components are missing, so those two would end up with zeros in their locations. Now, this would be the augmented matrix that we would be able to use in RREF. And I'm going to go to my calculator and enter those inside of a 3x4 matrix. So second matrix on this. Let's get this guy cooking. This is a 3x4 matrix entry. So a little enter, enter. And we've got 1, 1, 0 with a 0 down on the end. A -6 followed by a -3, a 1 and a 1, and then a 9, 0, 0, and -18 on the end. Now, what this should ultimately achieve is the answer for the RREF. So let's see what we get here. That's been edited. I'm going to go to second matrix again and math, finding RREF in the bottom of that math menu in matrices. And then I'm going to paste the matrix that we just edited inside that RREF, and it would generate these answers. Now, what I'm seeing here is the identity matrix and the values of A, B, and C that are listed there, and that's exactly what we see over here on the side, that A is -2, B is 2, and C is -5. Now, I wanted to show one of these to you, especially if we end up getting equations that extend beyond A, B, and C, but go to A, B, C, D, E, F, and you end up not wanting to do triple and quadruple elimination to try and figure it out. You can use row reduced echelon form to help you solve for those missing components. So I hope that adds a little bit of extra component idea solving to you, and it could be helpful in your stuff tonight.